Hi everyone, welcome to our live stream. This is episode 125, which is actually our 126th episode, and we're going to interview Jayson from Xilinx.
Yeah.
So I'll get right to it. We'll do a brief intro. So Jayson is the product line manager for Xilinx's cost-optimized portfolio. I'm having to read off here a little bit, which includes Spartan, Artix, and Zinc 7000 devices, and the Zinc UltraScale Plus MP SoC family. I looked up what MP SoC was. It is many core processor system on chip, SoC. So with over 20 years of Xilinx design, technical support, training, and marketing experience, Jayson leads the design of multiple evaluation boards, such as the Spartan 6LX9 microboard, Z-board, and Micro Z. So that's pretty crazy. I'm so excited to get started because 20 years of experience is insane.
With Xilinx?
It says 20 years of Xilinx design, technical support, training. So 20 years.
Yeah.
I guess we'll learn more. So switching over to Jayson. Let's see. Hi, Jayson. How you doing?
Hi, Sammy. Thanks for having me.
Of course, yeah.
Excited to be here.
Yeah, so excited to talk to you and get to know about what you've been doing. 20 years of FPGA experience is insane.
Yeah, well, yes, I've graduated from the University of Colorado in the mid-90s, and I did my senior design project was revolved around a Xilinx class device, so it's a 3000 series device, and I've been doing Xilinx designs ever since. I did design engineering for over 12 years, moved into field technical support, then marketing, and now I do product line management for Xilinx. And as you mentioned, I'm in charge of the cost-optimized portfolio and our ZU Plus or Zinc UltraScale Plus MPSoC family.
Right. So, well, that's, crazy. Can you, for our boards, the Matrix Creator and Matrix Voice, right, the Xilinx FPGA, we have a Spartan 6, is one of the most advanced kind of components, right, on our boards.
And we actually have two variations. The Creator board, which I have right here, has was it the first generation?
The first tier Spartan 6.
Yeah, and then our voice product has a second one, which has more memory.
It has more everything. Jayson probably knows. But yeah, we just for our viewers who may be kind of new to FPGAs, could you just tell us about Xilinx, what FPGAs are, and your journey with FPGAs?
Yeah, for sure. I mean, Xilinx has been around for 30 years, and the premise of what got us started is the fact that just you guys are perfect examples of what our perfect customer is, because you want to try and integrate a bunch of sensors or a bunch of different interfaces, or you need some custom logic to do something that a general off-the-shelf processor cannot give you. That's the void we fill. And we started out as an FPGA company. So FPGA is a field programmable gate array. So unlike an ASIC where you mask it and stamp it out and then you put it on a product, ASICs cannot be changed over time. Right. But we live in a world where standards and technology is changing so rapidly. It's a real costly and risky investment to go put everything into an ASIC and deliver that to market, because if you do, you're locked. And so with an FPGA, we're field programmable. So our customers can take their designs, move it into the field, and then decide and learn through their market and through their customers that a new feature is needed or a new resource or more performance, and they can actually dynamically give that to them without having to sell them a new product or go to a next generation device. Right. So, and again, back to that sensor integration, you guys have 8 microphone sensors on the board, you're driving a bunch of LEDs. It's hard to find an off-the-shelf processor that can do that for you. But you can have 100 microphones if you wanted. You can do whatever you want, right? Right. And we enable that. The direction we are changing as a company, and this happened about 10 years ago, we went from being a pure FPGA company to an SoC company. And what that means is we started to understand our customers, and our customers were taking our devices and putting them next to a processor or a microcontroller. And we started to think, if you don't integrate and innovate, you're going to die on the vine. So we thought, well, we could give our customers an incredibly much better design experience, if we integrate these two together, because so many of our customers were designing the discrete systems with the two parts on the board, the processor and the FPGA. They had to then architect the interface between those two devices. And when they architect those interfaces between the two devices, they have to understand how much bandwidth they need, how many signals they need, and they usually do that at the very beginning of their design process. They may find out, and then they stamp out the board and they start doing their design system, or they start designing their system, and they realize, oh, now I need more bandwidth or I need more interrupts, and they're stuck. But when we integrate these two things together in these SoCs, now it's all in one system, and you have more bandwidth between the processor and the programmable logic than you'll ever get in a discrete solution. And it's already integrated, and you can evolve it over time. So that has provided an incredible benefit to our customers, and it's just really ramped up for us right now. Our SoC product lines are the fastest growing product lines we've had in our company ever.
Right.
So we were even surprised by how much the adoption of it would be, how it would take off, and it has.
Right. So the SoC, so this is like kind of an interface between an SoC and an FPGA, or is it like soft core of an SoC on an FPGA? I'm like kind of new to it, so I just like have heard these things high level.
Oh, fair enough. Can I share my screen? Is that okay?
Yes, that would be great.
I will do that now. Let me know if you see it.
Okay, yeah, sounds good.
Do you see my slide with the cost optimized portfolio for embedded applications?
We see it.
What you can see here is the Spartan 6 device which you guys use. This is one of our most successful and popular FPGA solutions we've ever offered, and this gives our customers our lowest cost packaging and lowest cost per I/O device we make, and it is purely just an FPGA.
Right.
But in this device, you can drop in a 32-bit RISC processor that's a soft processor. We call that MicroBlaze. MicroBlaze has been in Xilinx for over 10 years. Every device I've ever designed for Xilinx, I have a MicroBlaze in there, because it's so easy to write the C code and update an FPGA with that C code and make it do different things. You can iterate much faster with C iterations and software iterations than you can FPGA iterations. So I have always put them in my devices. Starting in the Spartan 7 design, which is the successor to the Spartan 6, which you guys are using, we have now introduced the ability to add ARM CortexM cores. So you can use our 32-bit RISC processor, MicroBlaze, which is very optimized and very high performance. You can go up to 200 megahertz in MicroBlaze as a processor inside these devices.
Right.
And now we've added ARM CortexM. So we have an M1 and an M3 that you can download and put in these devices as well. So if many of our customers were nervous about MicroBlaze for one reason or another, but they had a lot of design heritage in ARM CortexM, and plus the ARM CortexM ecosystem is massive. They wanted to use those devices, those processor cores on our devices, so we provided that solution. Right. And so that now works on all of our devices. If you move up to our Zinc class device, if you see anything with the Zinc name in front of it, like Zinc 7000 or Zinc UltraScale Plus, we now harden the ARM processing cores inside the device. And the Zinc 7000 device has a dual Cortex A9s. We have a version with a single Cortex A9 and a version with a dual Cortex A9. So those are now hardened, and you still get the programmable logic to go with it as well. And there's a very tightly coupled domain between these two to maximize bandwidth and performance.
Right. So by hardened, do you mean like you can't change that part of the architecture?
That's correct.
Okay.
So exactly. So what you can see, what you get out of this, and I'll just kind of, I'll blast through these animations, but what you get, this processing system in the blue, we call this the PS, that has the single or dual core A9 processors in there. And then in that processing subsystem, you get all of the components you would typically see in an ARM class device, application or A9 class device processor. We add a memory controller, a flash controller, and a bunch of hardened peripherals that are sometimes hard to implement in an FPGA, like USB or gigabit Ethernet or or CAN. Those are types of interfaces that are generally hard to implement in FPGA because there's licensing fees and things like that. But we provide them all to you in this hardened system. And then, of course, you have all your programmable logic to add other things like gigabit transceivers, PCIe interfaces, ADCs, or anything else you want to add in there, or more memory interfaces, or whatever custom logic you have. So that's the flexibility we give our customers.
Yeah, no, this is super nice because actually recently we were trying to implement an I2C architecture in our Spartan 6, and it was a little bit harder than, I mean, I'm new to it, but I'm still trying to learn as I go and like create content for the community, and it was actually harder than I thought creating the I2C sort of from the ground up, the I2C sort of connection between the Raspberry Pi and say a GPIO on one of our boards. So like, you know, for future iterations of our boards, when we have like, you know, more powerful like FPGAs, like something like that would be really nice.
Like we upgrade from the Spartan 6.
Yeah.
Yeah, what I'm showing you now, one of the things we've done, and unfortunately, well, one of the things we've done is we made a radical change from our development tool standpoint about 7 or 8 years ago. Our primary design environment was a tool called I2C, which you're probably very familiar with Spartan 6. About the time that their 7 series devices came out, like our Arctic 7 and Zing 7000, we moved over to a new design tool called Vivado. It's something we're very proud of. It has billions of man hours gone into it to develop this product, but we have completely changed the way you develop embedded systems with our tools. You don't have to go through the old RTL flows, or you don't even have to be an RTL master, like a Verilog or VHDL master to even do this. You don't need to know any of that anymore. With Vivado, and I'm kind of showing a snippet of it here, if you want to add sensors or IP to a design, we have a graphical design tool called IP Integrator, and this tool allows you to pick IP and drag and drop them into a canvas where you can quickly stitch and add IP into a design. And things like I2C, SPI, UART, those are all in this catalog, and you can add and drop these in seconds. And our MicroBlaze cores and the ARM cores can also be added and dropped into this from the catalog in there. And all of our IP is AXI interconnect standardized. So we add these these AXI interconnect blocks. So all the addressing and memory mapping is done for you automatically. You can override it, but it is done there for you automatically. So it makes designs much easier. Unfortunately, this tool is not supported for Spartan 6 because the architecture was just different enough. We had to make a breakpoint, and that's where we kind of broke it. But the Spartan 7 devices are supported here and give you this flexibility. And almost all of our customers now are designing with Spartan 7 moving forward.
Yeah, no, that makes sense because the interface, it actually reminds me of my digital logic design class in college. We just had this like online tool where we're learning like digital logic design by dragging and dropping blocks, connecting wires, things like that. That's kind of what it looks like. So that's, you know, it's nice that you can kind of do a similar thing and actually program FPGAs using this developer tool, right? So
we actually had some users asking us about this development environment, and I don't think when we put the Spartan 6, I don't think the Spartan 7 was out yet, right?
I don't think so. When we first developed the boards, but definitely like for future iterations, like something that integrates with Vivado would be like super super nice. So there are some questions on the community, or like, you know, in the live chat. I'm gonna go ahead and ask some of them before you know, I forget. So Andres asked, he's actually one of our hardware engineers, there are plans for official support. Are there plans for official support for RISC-V soft cores?
That's a good question. We internally, well, RISC-V is first of all, let's be clear. RISC-V is an instruction set architecture.
Okay.
It is an instruction set architecture. So that's what is open sourced. That's what the community's all sharing. Now, to deploy that instruction set architecture on a processor, you need a processor that can interpret that instruction set. So again, what's really been open sourced is the instruction set architecture. There are third-party companies out there that are building processors to run that instruction set. And almost all the partners that we are aware of that are doing this are all prototyping their cores on our devices. I will call out one in particular because we have a good relationship with them, but it's called Sci-Fi.
Yeah.
So Sci5 is a company that is using our boards, the RD board that's shown in this picture here, to prototype one of their RISC-V processors. And they're great partners of ours, and you can evaluate their core and that processor for free on their site. So they go beyond that now. If you want to customize that processor for your own unique design, that's their business model.
Right.
So now I can't divulge anything what we're working necessarily in the future on, but we are right now relying on our partners to provide those RISC-V processing solutions.
Right, that makes a lot of sense.
Now, that said, there's nothing to prevent us from taking our MicroBlaze and running that instruction set architecture. So it is always something we're evaluating. We're monitoring closely the RISC-V development. We're seeing it how it's developed through our partners first, and if we do something with that, that's to be determined.
Right, that makes sense.
Yeah, actually, we have another question about the Spartan 6 and 7. Jack asks, for how long will the Spartan 6 be available? For a new design, should I target Spartan 7 or Spartan 6?
I guess asking if Spartan 6 is still a good option.
Yes, I mean, our opportunity pipeline for Spartan 6 is still growing. I can't believe it. It is still growing. Spartan 7 is outpacing it now, but it's still growing. It is being designed. And again, Spartan 6, from a cost per I/O standpoint, it is our best device. We will be supporting this device for production runs for probably another 8 to 10 years for sure. I've got commitments from our fab vendors to be supporting this for that time frame. So it is perfectly fine to start that for new designs. We have many customers doing it. We have taken our I2C design tool that you've used to use this. It's only supported on Windows 7 traditionally.
Right.
We've made a version of it that runs on Windows 10, and we'll update that forward. So because that is the only design tool to design these parts. So it will be around. Now that said, if Spartan 7 meets your needs, and I would definitely lean towards Spartan 7, because Spartan 7 is going to be a lower cost. Because it's a smaller, we're at 28 nanometer on this device, so it's a smaller technology node, and you're going to get way more performance. It's at least 40 to 50% more higher performance than Spartan 6. So, and you get the Vivado support. So if the Vivado support alone, for me, enough is the winner. As I was providing technical support in the past, there's all these wish list things we had that we could use to analyze designs, like clock domain crossing. It's that I2C didn't do that could do, but it was difficult. Vivado makes it very easy. You'll never have any clock domain crossing issues in Vivado. It'll detect it for you. So those are values for going for Spartan 7.
Yeah. So there is one more question in the live chat before I guess we continue. Do you have support for multi-core? I actually don't fully understand this question myself, which is why I'm stumbling a little. Do you have support for multi-core in free RTOS? What is the best approach for a real-time application using multi-core Zinc devices?
Great question. Okay. This is one of our major differentiators. Let me walk you through a slide here.
Okay.
This is what a lot of our customers do. They'll design with one of our devices, like a multi-core device, like a Zinc device. So the Zinc has Cortex A9 processors, has a single core and a dual core version, as I mentioned. When you look at a customer's application, you can break down their applications into really two types of tasks. Some that are non-critical but compute intensive, something like this middle task here. Okay. And some tasks are critical. They need to happen deterministically and in real time. Like the example I love to use is a drone, because we are in a lot of drones. And if one of your drone motors suddenly is out of sync with the others, you're going to buy a new drone. So these critical tasks have to happen all the time. Our industrial customers, our medical customers, our automotive customers all demand this. Right. So the problem is, in a scalar processor, you have a core, it has registers, it has ALU, it's processing commands sequentially. And as you maximize the performance of that, the bandwidth of that device, as you get to reach the limit, some of these critical tasks are going to start to fall off or lose their deterministic capability. So in Xilinx, without changing your device at all, without doing anything, you can just say, okay, I'm going to take the critical tasks and move them off to a coprocessor, like MicroBlaze or Cortex M. MicroBlaze has presets of it, without going into all the details of it, but MicroBlaze has presets that allow a microcontroller version, a real-time version, and an application version of MicroBlaze. So you don't have to know anything about building processors. We've given you these 3 presets because those are the common use cases our customers ask us for. So there's a real-time operating system version of MicroBlaze, and you can run FreeRTOS on it. FreeRTOS is a partner of ours. We have Micrium. We have many other OS providers out there, but FreeRTOS is free. Amazon now has support and plugins for it. And then you move all your critical tasks over here. So the beauty of this is that you didn't change a device, but as your application started to grow, these compute-intensive applications grew, you were able to move your critical tasks off to another processor inside the same device. And if you want to communicate between these 2 devices, Adam Taylor, who's a blogger for Hackster.io, he just today, I talked to him last week and we were talking about this, and today he just released his tutorial on how to do interprocessor communication with IP blocks inside our devices, like a mutex or mailbox. So communicating's there, it's all done. And let me show you one other slide here that's another great value in this system. What's really cool in our heterogeneous systems, whether it's a Cortex A9 or a MicroBlaze or a Cortex A53, and some of our devices actually have Cortex R5 real-time processors in them as well. No matter which device you're using, our SDK can heterogeneously co-debug these devices. And what's really great is if you have some function in your logic, some accelerator, some hardware function you accelerate, or some piece of IP like your I2C, and you're getting data back from the sensor that doesn't make sense to you, trust me, I've done this a bunch of times, you can just simply go into our integrated logic analyzer that's built into our tools. In Spartan 6 world in ISC, that was called ChipScope. Now we just called it an integrated logic analyzer, an ILA. But you can connect in there and you can set breakpoints from any of your processor cores and halt what's going on in the FPGA, or not halt, but capture what's going on in the FPGA and see what happened at that point in time. That's awesome. Debug that you cannot get in any other system. And vice versa. If something happened in your hardware, like you got a hardware stimulus event happened, and your processor goes off in the weeds, well, when that happens, you can set a trigger to go back to your software and halt or break the software. So you can see exactly what your software was doing at that time. This level of debug is way beyond what a discrete solution could ever give you. So when it comes to this, we support the heterogeneous multi-core systems from a design standpoint, and we support it from a debug standpoint as well. And in Vivado API, it's just as simple as you can drag a MicroBlaze down, you can drag a Zinc A9 processor down if the device supports it, or an A53 or R5. You can just drag them all into this canvas and then connect them all together through a shared memory, through through a mutex or a mailbox, however you decide.
Yeah, that's pretty cool.
No, it's definitely powerful with debugging tools. Without those, everything starts becoming a nightmare.
Yeah, I mean, the breakpoints are nice because, like you're used to doing that with any kind of software. So being able to have that with, like for C++ or C, you have breakpoints and it's easier. And, it's so nice to have it on the FPGA level as well.
Right,
so,
and I will throw one more note out about this. All of these tools to do this are free.
Right.
For the cost optimized portfolio.
Okay. We actually had a question about the cost
Somebody
of the
had
tools.
asked, so that's good.
And we've got, as you can see here, there's a YouTube video showing you how to do this, and we have a lab, a user guide with a lab in there that shows you how to do this as well, this code debug. So we try and give you all the tutorials and instructions you need to make you dangerous.
Right. Yeah, that's so awesome. I'm sure somebody who's more experienced with FPGAs is like, yeah, this is this is the best. But I'm just excited for hopefully trying these in the future. So there are actually a couple more questions. Do you want to ask this one?
Which one?
This one. Yeah.
Since you've been with Xilinx for so long, can you speak towards strategic/product thinking behind moving from shipping FPGAs for dedicated hardwares to SoC? And all things programmable. I have.
Yeah, I guess. So, should we repeat the question?
I got it. I mean, I've kind of already answered that one, but the shift from just a pure FPGA company to an SoC company was really driven by the demand of our customers.
Right.
What I've just showed you from a code debug standpoint, from a bandwidth standpoint, from a flexibility standpoint, a
Right.
future-proofing standpoint, that's what drove us in this direction, and we are here to stay. Everything, almost every part we're building now has some kind of embedded hardened processor on it. And if it doesn't, like the Spartan 7 family or the Arctic 7 family, I'm actually looking at introducing another next generation family here, which we'll hopefully talk about in the future.
Right.
But that one too, that'll be a pure FPGA as well. But that, if you want to add these processors to them, you're welcome to. A MicroBlaze or an ARM CortexM or a RISC-V. You be the guy. You decide.
Right.
This slide I'm showing now kind of shows you that scalability we give you across our platforms. Everything from a Spartan 6 with MicroBlaze, and again, it should have ARM CortexM and RISC-V on there too. But you can just replace MicroBlaze with soft processor, and you can see how we scale up the processors. Everything, the dark blue boxes are all hardened processors. And we even add GPUs and video codecs into some of our bigger devices as well. So depending on what the customer needs are, we can scale up with your customer needs.
Right. Yeah. That's so basically like a lot of most people who use Xilinx FPGAs they go into production like it's for a more commercial product, or do you see a lot of just kind of the developer community, like how is that sort of You mean
like what's a developer community towards the production community like
makers to I guess more production, right?
Right. Yeah. It's that's a tricky one. We've been around 30 years and our company's growing. We are you can see it in our stock portfolio, but it's growing, and we're always innovating. We pride ourselves in innovation. In fact, you can look at our financials and you can see we invest a heavy amount of money into our R&D. So we're always developing new products. We're the only company in the world that has quad A53s, a VCU, a GPU, dual R5s, and an FPGA built into the same device.
True.
We're also, and we're not even talking about it in this call, but we have another device that goes to the right of this one. It's called our Zinc RFSoC device, and that integrates gigabit sample ADCs and DACs. Nobody in the world has done anything like that. So we constantly innovate and invent. So we do this, for the commercial space mostly, because that's where we get lost. But we are definitely putting more focus into the community space. We are working now, like I said, with bloggers like Adam Taylor, who's excellent, and he's got a chronicle. When I built MicroZ back in the day for Avnet, he started writing these chronicles on there on how to do different things. And anything you can think of doing, he's done it. And he has over 250 tutorials on this. Now he's blogging for Hackster and doing more things like we talked about before. And so we're using companies like Hackster and bloggers like him and Element 14 to do design competitions. We did a pathway to programmable event last year with them. Things like this to really seed the community. And we actually have a website now we're building a website right now. We've got it out called xilinx.com/community, and it is where we're going to start posting some open source IP and people and community projects, and everybody can start collaborating there. That's what we kind of want to do.
That's awesome. So I mean, given all of this, community projects that are coming out, what are some of the kind of really cool ways you've seen the community develop with Xilinx FPGAs, and how would you sort of say somebody who's trying to get into it, how would you say they can start, or what projects do you think they could try out as a maker or developer?
Yes, great. I would definitely look at Hackster.io, Hackster.io. And you just search Xilinx. I look at it every day. There are new projects every day coming out there, and that's where I'm kind of guiding people to, and making that our kind of common point to go to. There's everything from robotics to voice control. You guys are a great example too. The cool things you guys are doing from an open source standpoint on your voice control, and you're even doing the machine learning with the gesture recognition and things like that. One of the things we didn't talk about here And I don't have a slide for it, I don't believe, in this deck, but we bought a company last year called DeFi. And DeFi, what they did, instead of dropping a MicroBlaze a soft processor in the fabric, they built a neural network processor that drops in the fabric. It's called the DPU, and the DeFi processing unit. But it is a neural network. It's a configurable neural network processor. So you can think of this like a CUDA core from NVIDIA. But when you buy an NVIDIA device with CUDA cores, they are fixed amount of CUDA cores inside that device. So if you want to do something bigger, you have to move up to a bigger device. With us, because it's all in the programmable logic, you can just scale your neural network processor for as many resources are in the device.
Right.
And what DeFi figured out is that these neural networks are very common. That the architecture and how they're built is very common to what our architecture is in our systems. And they just built a processor that built around it. And they have a whole development flow to take anything from Caffe or TensorFlow for any of these framework level device frameworks and bring that right into your Xilinx device. And we have tons of tutorials on that on our site. There's lots of customers on Hacked.io who are deploying this. And because we have that co-process, now you can have a really heterogeneous system now, all in one device. And we are dumping a ton of resources into this. Into the community and to our support for these types of applications. But machine learning is growing faster than we ever imagined right now for us.
Yeah, no, machine learning is growing super, super fast.
It's currently a hot topic going on.
Yeah, and you know, there's just like a lot of things you can do with it. So, you know, lots of different applications. So there's a relevant question. Do I need the processing system to use the DPU, or could I use it on a device that is not a Zinc?
Good question. Right now, it does need to be on a Zinc device, and it wants to run Linux because that's how they do the partitioning, and that's why they do the hardware-software partitioning. So some of the software will run on the Zinc, and some will run on the DPU. We are investigating, and this is not plan of record, but we are investigating a similar solution to do this with MicroBlaze. Okay. So it'd be a MicroBlaze with a DPU. We have not productized that. We are only investigating that right now. It can be done. It's just how, and I think there's people in the community who've actually even tried to do it, but we are looking at productizing that ourselves.
Right. No, that's really impressive. Yeah, there've been a lot of questions. Just like little FYI, like this has been the highest view count live stream we've had so far. There were 41 people at some point, like for live views. Yeah, which is crazy. And there's like a lot of good questions in the live chat.
Yeah.
Yeah. So there's another one.
This one's from our hardware engineer. It says, ISC has been free since 2014. What do you think about open source synthesis tools like Yosis?
I guess Yosis, yeah. YOSYS.
There's a few of them out there, open source synthesis tools. I know the open source community. I've worked very closely with a 3D printer company here in Colorado. You could probably guess who they are, but they are strongly open source driven, and they are using devices, of course, like this as well. I can't say much about them, but but yeah, this open source community is something we want to start supporting more. But you understand, we do have a customer. We are a publicly traded company. We are accountable to our shareholders at the end of the day, and we have threats of other startup companies that are evolving. And our XST tool, for Xilinx synthesis tool, that's in ISC, again has hundreds of millions of man hours into it. So we have kicked around the idea of open sourcing it, but it's at this point in time we cannot do it. Actually, and the real reason why we cannot do it is because some of our tools are under the embargo agreements with the United States government. So we can't just open source, because then we go into countries that we cannot trade with right now. And then therefore, that's when you look at our license agreement, when you look at these tools, that's what it revolves around. So it's not even, not to say that we don't want to do it. It's like sometimes our hands are tied and we can't do it.
Yeah, we know all about legal issues being barriers. But yeah, no, that's, you know, it's good to know sort of, because, you know, a lot of the times people, like, the open source movement is big, right? So people really like open source stuff, and sometimes it's good to know the reasons behind why something you really like might not be open source. So wow, we've had lots of great questions. I've lost track of the questions that we had.
One of the questions I was to say about the open source thing that I get stuck on with customers is we do get criticized sometimes because our tools are not open source, and part of the open source edict is that the whole design flow must be open sourced.
Right.
But if you went and bought a Cortex, you bought an ASSP, an off-the-shelf processor, you didn't have the tools to build that. And even though you're running all your open source tools on that device, you didn't have the tools to build that either. So at the end of the day, I can give you a pre-built application with a Zynq and a MicroBlaze and a DPU all in one and give it to you. You never change it, and it'd be no different than you just buying that off-the-shelf processor.
Right.
So I know we can't open source those tools to how you build it, but you didn't get the tools that NXP or Renesas or ST Micro did to build their devices either. You just got a device that was fixed. I can give you a fixed device too. It's not it's still interesting, but it's not as interesting as it could be. So we can compete. If you look at apples to apples, we can give you the same thing that any processor company gives you. But nobody really wants to use this if they can't configure the custom logic to do something or that they want to make that's unique or something that's new.
Mm-hmm.
Yeah, that makes sense. Okay, so
more questions?
There was one more question, but it's kind of been answered. Somebody asked about Spartan 6's future, and you seem to say that, it's gonna keep going for a while, because there still is development for Spartan 6, which is good.
Just out of curiosity, are there any open source solutions made by the community that anyone you know from your team uses internally?
Interesting question.
Well, all the frameworks. Right, the high-level frameworks. We have a solution for Python. It doesn't work for Spartan 6, but for our Zynq class devices, we have a Python solution on Zynq. So it basically takes, like I was telling you, we give you a platform that has a Zynq processor and a MicroBlaze in the fabric, and we call this our Pink device, our Pink board. It's Python on Zynq, and then from there, that's the whole point. The whole open source community can program our devices, our devices right there, and we use Jupyter notebooks, and with that, you can call any OpenCV, all any of these libraries, and run these on our devices. So,
right. Yeah. So I'm excited to look more. Like, we love Hackster. We we post all of our projects on Hackster, and we really want to develop more with our Spartan 6. So. We gotta look at Hackster to create more for Hackster.
Yeah. And since our voice boards have was it bigger memory, more?
They have more DSP slices and more lookup tables.
Yeah. So potentially we have a lot of room to utilize our FPGAs on our voice boards to add in all kinds of neat features.
Mm-hmm. Yeah. So because there's the Raspberry Pi to our GPIOs, or basically you can use through the FPGA. It's so fun to route different Raspberry Pi pins to different parts of our board, and I mean that's basically what's done on our board currently, but you can also do it custom in your own way, which is pretty fun to play around with.
Right.
Yeah.
Right. And think about that in your DSP resources. Here's one plug for Spartan 7. If you look at the 25,000 logic cell device for Spartan 6, it has 38 DSP blocks. Spartan 7 in the same packet, or same density, 25,000 logic cells, has 80, more than 2x. So we made the Spartan 7 class devices more concentrated for performance. Because machine learning blocks, the DPU uses these DSP blocks. Anybody building filtering uses these DSP blocks.
Right.
And again, we have graphical tools to show you to build these things for you, so you don't have to sit and stitch all the little wires together. Just you say, I want this type of filter, and we'll build it out of the blocks for you. But you need these blocks to make them run fast. Right. But yeah.
Yeah, I mean, I'm excited to learn more about, just how everything's working and, how it's all going. Oh, somebody said it would be nice to see Matrix Voice 2 with Spartan 7. And our hardware engineer said, I agree. So that's good.
We'll see in the future what comes up there.
Yeah.
Well, I'll ask you a question. I'll flip it back on you. I saw on your creator board, you have a Spartan 6 on the back side, and you have an Atmel device on the front side.
Yes.
So there's a classic example of customer we talked to where, why did you put I'll flip it back to you. Why did you put an FPGA next to a processor when you could have just bought Zinc and done it all in one?
Right. Our hardware engineer is watching, so Andres, please answer.
I mean, off the top of my head, when did the Zinc come out? After, way after the Spartan 6, or was it around the same time?
Yeah, Spartan 6 has been around, I think, around 15 years. Zinc's been in production for about 8 years.
Okay.
So Zinc is a newer product.
Okay,
Gotcha.
yeah. I mean, maybe that might have had something to do with it. But yeah, our hardware engineer may or may not be answering right now. Oh, but one of our other team members asked, how interchangeable are the Spartan 6 and Spartan 7, like PCB design-wise? I guess we're already trying to get more information from you on how easy it would be to switch those out.
We did try to make these as compatible as possible. However, there was just enough architectural changes. The type of technology we use to build the die itself is different.
Right.
And so we that is one thing. So the power and grounds and things like that changed. We wanted to get our bandwidth up on our I/O. All of our I/O can push over a gigahertz. I mean, that's incredible too. Mm-hmm. And so that took some change requirements there. And then in most of the Spartan 7 devices, we've hardened in more peripherals. We've hardened in dual 1 megasample per second ADCs on the device, and we've also hardened in security blocks. So customers of yours who might use your devices and they want to encrypt what's going in and out of their device, you need the security blocks. And so we harden those as well too. Right. So those are things we add in Spartan 7 that didn't exist in Spartan 6.
Right.
And so those changes make it a little bit of a change to do. But from a packaging standpoint, we offered mostly the similar types of packages and sizes. And and the Vivado tool makes designing this much easier than ISE did.
Right. So just because of those different hardened parts, Spartan 7 and Spartan 6 isn't as simple as a pinout change, or you can't just swap them. They're not
right.
Yeah. Okay. Gotcha.
But we still keep all of our. Well, if you're a text level entry type person, we did switch from in ISE from a constraint format called UCF, which is a Xilinx proprietary type constraint format, to an SDC, a Synopsys design constraint format for all 7 series and newer, everything Vivado. We've made a superset of SDC, and we call it Xilinx design constraint, so XDC. But we've added more things that are more FPGA centric. But it's all text file, and it's easy to read. You can easily take a UCF. We even have a tool that will convert a UCF to an XDC. But you'd still have to match the pin out to the parts. So that does take a little bit of work, unfortunately.
Right, yeah, I got you. So somebody asked, Spartan 7 doesn't have any transceivers. Will we see this in future Spartan devices? Great
question there, too. This does come up a lot. We weren't very clear of that. Unfortunately, what we did in the Spartan 6 family is we confused everyone. Because we made 2 devices in Spartan 6. We made a device called the Spartan 6 LX, and then we made a device called the Spartan 6 LXT. Okay. So if any device had a T suffix, it had transceivers. But then that kind of confused customers. So in the 7 class, the 7 series devices for us, we have the Spartan 7 and the Arctic 7. The Arctic 7 devices add the transceivers. The Spartan class devices do not have the transceivers. So fundamentally, these are the exact same architecture. They're both 28 nanometer and have the exact same internal architecture. Just the difference is one has transceivers, one doesn't. So Spartan 7 won't ever have transceivers because the Arctic family is that. It is basically a Spartan 7 with transceivers.
Got you. Okay, that makes sense. Yeah, I've been thinking a little bit in the back of my mind about the ARM Cortex M3 with Spartan 6, and potentially one of the factors was maybe cost. I don't actually know how the costs compare, but that could be a factor as to why we chose to do that.
I mean, we got to ask Andres. He's the one that designed that.
And then also maybe the Zinc might have been too powerful for our board. That's also possible. These are just things that I'm coming up with. Our hardware engineer would know exactly why. But yeah.
Right. And while these blocks on my screen are showing steps going up. That's not cost, it's really performance.
It's performance, yeah.
But Spartan 7, when we built it, I had the design constraint put on engineering teams that it needed to be similar or less cost than Spartan 6. So if you took two very similar parts, put them side by side between the two families, Spartan 7 should be cheaper.
Right, I see. Okay.
So a lot of times you see family parts come out and they get a new next generation something and it's more expensive because it's giving you more. It's more performance and lower power and all these things. We didn't. We said, let's keep, this is the space our customers need to play in, and this is the price points they need to meet, and we try to stay in that range despite giving you ADCs, security blocks, 50% more performance, 30% lower power.
Right.
We still kept the price the same.
Yeah, no, that's awesome. So, I mean, I guess that kind of ties into our last question that we had prepared for you, because we had so many great questions off script. Not script, but, off of what we had thought of before. So talking about design constraints, when you're coming up with new designs for FPGAs, what generally drives your design decisions? Like, obviously some input from customers, but what other things are drive your design decisions and your process?
Yeah, that's a great question too. Again, my focus is on the cost optimized portfolio, or our consumer based devices, and high volume or more high volume type devices. So you can guess in my area, the things I'm always balancing is price, performance, and power.
Right. That makes sense.
So, and you're not to spin off it, but to give you an example, if you're in a car these days that's driving around and it's doing lane detection and auto driving for you like that, there's a very high chance that a Xilinx device is behind that. So most people don't know that because you don't crack open in your car.
Yeah.
And we are the next generation of these self-driving cars. We are very engaged with our customers. So to meet, so our customers can often demand or dictate our direction we go. We want to provide solutions for these markets. And so we integrate things like, you can think back to Spartan 7. Why did we started hardening the security blocks inside the devices? Because when you have a field programmable device, you better have security these days, or somebody's going to hack it. The whole entire Eastern Seaboard was shut down 5-6 years ago because the people hacked into baby monitors and started doing a DOS attack on the East Coast because they didn't protect any security blocks inside. They had no security inside the device.
Right.
So we hear that. We give it to you, and you could have built that in the logic before. You could have built these blocks in logic. That's what people did.
Yeah.
They built these encryption blocks. The problem is that cost you a lot of space in your logic and area, so we hardened it.
Right.
Things like that. We make those kinds of decisions based on what the cost of resources are from a logic standpoint versus hardening, and then how widely adopted it'll be.
Right.
And so the DPU that we have from DeFi, right? Well, you may have just seen we just announced our next generation device, a 7-nanometer device called Versal. And guess what we hardened in Versal?
Security?
The DSP?
It's not the DPU. It's like a DPU, but it's an AI engine. It's an AI engine. So we hardened an engine in there to do machine learning and artificial intelligence. Because we had the soft version for a while, but it'll go faster if you harden it and give you lower power and more performance. So those are the things that kind of drive these decisions. But like another great example I'll give you is we have support for like MIPI in our devices. A lot of people don't know that. And so our new board that we just released called the Spartan 7 SP701, we're releasing it this month. It'll have MIPI, CSI, and DSI interfaces on it. And you can use an ARM CortexM or MicroBlaze to handle that video, and that's why we want to add a DPU to this as well. And then you could do some video analytics and things like that natively all in one device.
Right. Wow. Yeah. This is all. That's real. So it's like a balance between hardening, having programmable parts. So that's performance, and then all of that combines to performance, and then there's cost and. Yeah, that's pretty crazy. It's interesting because, when you think like FPGA, the first thing I think is it's all programmable. but you gotta have some hardened parts to make it easier for people to, use it for their application without having to develop every little thing that's already out there.
Right.
So that makes sense. So that's really cool. Wow, there's a lot of great discussion happening in the comments. This is this is really fun. So
Any new questions?
there aren't any new questions, but somebody was just saying, should we talk more about the DPU technology? Smiley face.
Well, that is another day for a conversation.
Yeah.
But I try and fairly regularly put out webinars.
Right.
And I did one on how easy it was to use MicroBlaze about a year ago. I did another one on Cortex M a few months ago. We had over 2,000 people register for that webinar, so that was pretty well received. That just shows the interest level that people want to use on our devices. I use these Cortex M cores on our devices.
Yeah.
I think a future one I will do is probably revolving around the DPU. So stay tuned for that. But we have lots of quick take videos on our website on the DPU. Our documentation, we are scrubbing and revising that documentation weekly
Awesome.
to make it easier to show how to use. And we have a portfolio now of, I want to say, over 100 DNN type architectures that are just downloadable, ready to use examples. And we're expanding that every day. I mean, we are... that's the beautiful thing about the machine learning, why we're so great for it, is that the topologies for these neural networks change instantly.
Right.
One day you're doing image classifications with CNN, or better yet, let's just switch it to your mode. You're doing voice recognition with a BNN or something like that. The next day, everybody's using LSTM, right? And so the architecture changes, the topology for the network changes, and I guarantee you next year, it's going to change again. And so if you cannot build a device that can change like that other than an FPGA. So we can take that DPU and just build all those neural networks however you want, and we can do them all. So and as they change and adapt, so can we.
Right.
So we will have some tech talk on that in the future, I believe.
That's awesome. Yeah, looking forward to that.
We actually heard when we went to the Bay Area Maker Faire, we've heard about some developers, when they program FPGAs, they program a lot more reserved than they have to be because they're so used to programming on chips where it's, you program it once and you're locked in rather than you can go back and edit it.
Yeah. I think people forget how flexible FPGAs are, and I think they're, for new people, also speaking for myself when I first started, there's this sort of fear that you might short something or break something, if you do something wrong. Which is probably not
They're
true.
pretty hard to break.
Yeah.
I mean, we have constraints. As long as you use our design tools, we prevent you from doing those things.
Right, exactly. Which I think is kind of the fear newbies have, but it's good to know that you most likely won't do that.
Well, another thing along those lines, when it comes to designing software, the two major methodologies of design software are the agile method or the waterfall method, right? And we're changing people's way people do things because you don't have to have it right the first time. You can evolve, and so you can be more agile. So we're changing the way software methodologies work as well with these devices.
Right. So to be respectful of your time, there's this one last question we'll ask, and then we can sort of wrap it up.
Sure.
So somebody, Jack Hundley, asked, why did Xilinx decide to put the Cortex M3 in Vivado? Isn't it competition for MicroBlaze?
At the end of the day, we don't sell MicroBlaze.
Right.
It's free. It's royalty free. You can do whatever you want with it. So, and we haven't open sourced that yet, but never say never.
True.
But it's free, and we've never really charged for it or licensing. We kind of did for the SDK back in the day, but it's all free now, and we're no plans ever to charge for it. It is a vehicle for us to sell more silicon. And so whether you choose MicroBlaze, ARM CortexM, or RISC-V, I don't care.
True.
So realistically, the ARM CortexM one, we've been working, we're great partners with ARM. We've been designing their A9, A53, R5 cores into our devices for 8+ years now, right? And we're great partners with them there. We work very closely as the two companies. They actually prototype, and many of our customers prototype their future next generation ARM cores in our devices. So we're building emulation devices for them to do that. So it's very symbiotic.
That's super cool.
Yeah, I don't care what anybody uses. We support them all. If your preference is ARM Cortex-M, do it. And we worked with them for a long time to optimize those Cortex-M devices for our parts. So you can get a Cortex-M1 running over 100 megahertz inside our device. That's pretty good. You can't buy an off-the-shelf Cortex-M0 running that fast. So, we've done a lot of work with them to make this efficient. And like I said, and those, by the way, those Cortex-M1 and M3 cores, they're free as well.
Yeah.
You don't have to pay for those either. Yeah, no licensings, no royalties, nothing.
We were super excited when that IP opened up. We were like, wow. Okay.
And the one that just asked a question, Jack, thanks you so much for all the time you put into putting his answers.
Yeah. All right. So I guess the last thing, is there anything else you would want to share with our viewers? Any words of advice for FPGA developers or enthusiasts? Just, closing remarks, I suppose.
My closing remarks would be one of my missions when I came to Xilinx. I understand where everybody's come from. I did design engineering for 12 plus years. I understand you get into a Xilinx device, it doesn't seem as trivial or easy as a Raspberry Pi or something like that. We have a lot more flexibility, and with that flexibility does come some complexity. But it's my mission to make these devices easier to use. And I'm going to keep striving forward towards that. And I have plans that we're putting into our tools to make them easier to use. This IPI design entry tool, it allows software engineers who have never even touched RTL code, like Verilog or VHDL, to design a complete custom embedded system quickly and easily. We're making tools to translate C code into RTL, so you can take you can port over your application from Raspberry Pi, profile your application code like you do on Windows, and see what function or application is consuming all of your memory. What is compute intensive, like I showed you earlier. Mm-hmm. Profile and say that's a compute intensive task, and then we can analyze it for you and say, should that be in the hardware, accelerated in the hardware,
right,
and not run on the processor? And if you say yes, we will port it over to you for you automatically.
Wow.
Even build the DMAs in place to connect back so it can communicate back to the processor. As far as you know, as a software engineer, you don't even know where it's running. You just know that the code ran and it went way faster. And so that's the things we're doing, and we're constantly improving those tools. And I'm trying to get more IP into our catalog so that you can just drop and drag as much as you want, and then build a quick system in minutes, not days or weeks like it was before.
That's awesome. Yeah, that is like the developer dream.
Yep.
So very cool. It's so great. There is one last question. I don't know if you have time for it.
I've got a couple of minutes, sure.
Okay. So is there an effort on LLVM side?
I'm sorry?
I mean, the question is there an effort on LLVM side? Which I don't really know what the question means, but I'm hoping you do.
LOVM?
LLVM.
LLVM, I'm not sure either. Can they clarify?
Let's see.
They're
Can you
asking right
clarify? LLVM. Huh. Trying to think. Is that something I know? It sounds familiar. LLVM compiler infrastructure project.
Yes. Okay, now I get it. Yes,
Okay.
It's a compiler infrastructure. We do not have. I personally in the company am not working. We do have a software solutions team that might be doing some work with them. I'm not familiar if they are working with them or not. Or that flow. So I'll have to avoid that question because I don't know the answer to that one, I'm afraid. Sorry.
Yeah, no, that's okay. Sounds good.
No, we understand.
All right. Well, oh my God, this was amazing. There's so many great questions, so many people interested, having just discussions in the chat, and your answers and your explanations were great. I mean, I'm an FPGA noob, and I was like, wow, I gotta look up this word, and and I felt like I learned a lot. Yeah.
I mean, you could definitely gauge the interest because this is. For all of our live streams, this is the one with the most most live viewers we've ever had.
Yeah, and most sort of like engagement. Like people are asking questions, having discussions. They're just like people are enjoying all this content. So thank you so much for joining us and giving us your time and your brain. It's great. So yeah.
Absolutely, I appreciate the time too. Thank you very much for putting this together.
All right. All right. Well, hopefully we'll speak again.
We will.
All right.
All
Bye,
right.
Jayson.
Bye.
Thanks,
you.
everyone.
Thank
Bye.
you. All right.
Okay.
So I'll just switch to the front camera and we'll close out. So that was a really cool live stream. I'm still like, kind of sifting through the questions. Okay, awesome. Yeah. So this camera, right? That was really cool. Thank you everybody for joining us and asking all these great questions. Great engagement and
Yeah. We learned definitely a lot more than I knew about FPGAs before because I never really got into them. And well, I mean, might as well start now, but never actually been much of a hardware guy. So with the whole software initiative and the community initiative they're doing,
right,
it's definitely going to be easier.
I mean, you probably don't even have to know exactly how the hardware is working with the Vivado tool or, some of the things he was talking about where you're like, okay, I'm doing this stuff on the Raspberry Pi, let's put it over to the FPGA, right? You could, like, as a software developer, do that, like, yeah, so
this was episode 125.
Yeah, and I guess that's it. Thank you for joining us.
And,
I won't go over announcements. We'll just do that next live stream because this one was, a really nice long one. But thank you for watching and hope to see you next time. Bye, everyone.